So I'm the CTO of DigixGlobal, and I am famous for basically doing the first ever Ethereum transaction on block number 46147. And I'm here going to talk about contract patterns and security. So the key points is, first, solidity is not broken. Okay, so a lot of people, there is some plot posts in the past saying that solidity, because it is an imperative language, that it's a poor choice for writing contracts that has like state transitions. So I'm gonna show you guys that just with proper tooling and architecture, we can actually write secure and easy to manage contracts. So we're gonna use, I'm gonna show you guys code patterns that allow us to minimize attack surface. And I'm gonna show you guys the contract execution flow and figure out how you guys can identify attack surfaces in your contracts. And also I'm gonna go show you the case study of the DigixGlobal's contract architecture. Right, so both right, so the bold claims. Quote, good software design requires, basically gives us secure, good security. So if you write, if you have good architecture, you'll be able to actually create easy to secure and easy to audit code. The first point is that good readable code and good architecture, which is that can easily be reasoned to, can be read by an external auditor. So if you send your code base to a third-party auditing company, they can actually easily read your code without having to deal with spaghetti code, right? So we know that if like this type of code, well, if you send this to somebody, it's going to take a while for them to parse through this, and that makes auditors' lives so much harder. And two, like good software architecture will also allow us to actually have reusable battle-tested code. So basically, we can take components and build them out individually, and we can reuse those components for other parts of our contracts. And since we know that these are battle-tested, then the security, we know that the security is good. So good software architecture also allows us to have separation of concerns, which actually enables the second point as well. So if you separate your code logic into separate contracts, in the case of Ethereum, then it's easier for you to audit it. And it's also easier for you to control the attack surface, the potential attack surfaces on your contracts. All right, so I'm sort of want to make the analogy of an electronic circuit versus software. So in like an electronic hardware, for example, a computer motherboard or a CPU, once that's created and fabricated, it's very difficult for the manufacturer to recall those products. So basically, in essence, like Ethereum contracts, when you deploy them to the blockchain, you can never change them. So in essence, like we're expected to become electronics engineers when you write contracts on Ethereum, right? So here we have Commodore 64 motherboard. I don't know if any of you guys are familiar with this old school computer motherboard. We have the series of memory chips and the MOS sound chip, the interfaces. So when you design hardware, you have different components that are known to work well, and they've been tested, and you just basically put these things together and you have a device. So basically that sort of falls into the same concept as a software development paradigm called design by contract. And I'm not talking about solidity contracts here, but basically creating your software based on small components that multiple people can work on or multiple organizations can work on, and you have basically a set of preconditions that you can take in, and that will either produce a side effect or an output value. Fairly simple, right? So basically, if you can make an analogy, this is sort of like your sound chip or your CPU. You can put input in it, and you have expected output from it. Next one. Where am I supposed to point this? I think the battery in this is dead or dying. Do you guys have another controller? Yeah. Yeah, the top button is not working. Sorry about that, technical difficulties. Thank you. Rewind. All right. Back here. All right. All right. So the third point is separation of concerns. You basically separate your contracts into small pieces that can be easily audited. And you basically can define the entry points and exit points to your contracts. And number 4, good architecture will allow us to actually write better tools, such as static analysis tools and generators to create, basically help you create boilerplate code to implement this, this approach. So what are attack vectors? Right, so attack vectors are basically code paths that allow a malicious user, such as a hacker or somebody, a user that sends unintentional code to your software that either gives them unauthorized access. And these can, in traditional software, you have command line arguments where you can pass like a hacker can pass a carefully crafted code, such as a shell code with some buffer overflow exploits, and basically give them access to that machine. Environment variables as well, and URL parameters, which is common in web application hacking, where you can basically have a hacker send SQL injection commands into your application by basically sending a carefully crafted post data or URL parameter. And also data storage, which falls in the same concept as the previous post of URL parameters. In this case, somebody has access to the database, and your application reads some data from that data and causes your application to behave in a way that you were not expecting to. And in the case of Solidity and Ethereum contracts, these are function parameters and third-party contracts that can access your contracts. So let's look at the Ethereum transaction flow. So we know that all Ethereum transactions must happen from an externally owned account. That means your private key. So in the first 4 examples, you have an externally owned account calling an Ethereum contract. And that can go with an Ethereum contract that pays out to another externally owned account. And the third example is an externally owned account that sends a transaction to an Ethereum contract, and that also calls another Ethereum contract. And that is basically where you see things such as recursion and reentrancy problems, right? And then the fourth one is just basically somebody sending Ether to another externally owned account. And the last 2 can't happen, right? Because like contracts cannot basically start their own execution. Maybe in the future. So let's look at the example ERC20 token. Here, this is actually on the DApp bin. I just cut and pasted this. And this is basically the standard token format, standard token code with the standard interface for it. So here we have the contract, and then you have send coin function, which takes some values, coin balance, which shows you like the balance of the account from the mapping, and then you have the balance off and approve. And so you have all these functions, and they all reside in the same contract, right? So it's in the same binary that once deployed on the blockchain, it's immutable. You can't change it, and it's very difficult to have people point to a different contract address. So what we're going to do is we're going to break down the contracts into pieces. Basically, these are components that behave in a certain way, and you can basically describe your software just based on these contracts. So we have interface, controller, storage, and the last two are basically what glues everything together. We have the access control and the directory services and resolver. All right. So interface contracts. Contracts that be called directly by an end user or external contracts. This is the main entry point, right? So basically, this is the contract that when you compile it and you produce the JSON ABI, this is the ABI that you put onto your MISC wallet, or you give to your users or to other people that will be using your contracts. So this is the main entry point. So for our design, this is the only attack surface. So this simplifies a lot of the security audits and making sure that your code is secure, because this is the only entry point. And we can control this a lot better than having a file that has all the logic in one file, and this can get overwhelming when you read it, right? So if you're dealing with 400 lines of code or 500 or 1,000, it's overwhelming to read one file, and you can't really, it's hard to reason about like large pieces of information. So if you break it down to smaller pieces, it's a lot easier to reason about it and figure out what's going on. Rewind again. Am I just having the worst luck for this? Rewind. Right. So interface contracts, talk about it. Control contracts. Basically, this is where most of the code logic goes, and this is where you basically have the interface contracts calls this, basically, and all the functions that are needed to be called that basically either change storage state, the state storage, or does some calculations are all in here. So most of your logic is going to be here, and if you wanted to look for logic errors, this is where you would look for, right? Storage contracts. Right. This is basically your database, right? So in traditional MVC, this is your model. This is where you put all your data, and you put basically this is where all the information is about your contract and the state of your DApp. Other components, access control. This is actually a very important piece that actually puts everything, basically this is the biggest piece that puts everything together. And this basically a set of reusable code that we can use to describe how a resource can be accessed. And at DigixGlobal's, we sort of identified several access control patterns. Basically, these are how you describe how a resource can be accessed by an externally owned account or another contract. And so that would be an example here is the AC-owned contract that we have, and it's very straightforward. There's a contract that has an owner, and if the sender of that transaction is the owner, then let it through, and if not, then you throw an error and eat up the gas that they sent, right? And then here we have it's very small, the groups. So basically this is the same as the owner, but you can basically define multiple users to use to basically say that like this this resource can be accessed by these addresses, and it's basically a simple mapping that says if you're in a group, you can access it, and there's like some functions to add and register users or add groups to the system. And the directory service. This is what puts everything together. It's basically a key value store. It's its own contract storage, and it tells the other contracts. Because now we have split the contracts into multiple pieces, then you have a directory service that tells you basically where those contracts reside. So in our directory service, it's pretty straightforward. It's just a mapping of some byte string and the address. And we can resolve it. We can register and get the values, right? And we have, if you can look at this second function here, or the first function, I guess, if group NSAdmins, it allow you to do that, call that function. And then we have a resolver client here, which is basically a, this is your name server resolution client. Allows you to figure out where the contract, what the contract you need to call is. And if there's also a modifier check, basically to say that if I'm being called by this contract, based on its byte address, or its byte string, then allow me to go and do what I want to do, right? So, sorry. So, directory service. So here's the resolver. So here's the meat of this whole talk, really, is the ICS pattern at DigixGlobal's. So here we have the TX origin. This is the entry point. This is your attack surface. And this is where you would look at where a malicious person would attack your application, right? So you have your group access control, and you have your, in DigixGlobal's, we have like different interfaces for different roles on the system. And the directory service bus tells those contracts where to go next. And you have the storage at the bottom. So the storage basically, if you look at this design, you can basically easily change these contracts and update them and add new functionality or fix a bug by just actually changing the value on the resolver. So the only thing that's really difficult to change are the storage contracts, because that's where all your state and previous state is on there. So if you have a token contract and you have your ledger information on there, then that's kind of difficult to change. But there's ways to
Anthony, do you have the information for where people can find more information?
So so this is basically a call to action for people to contribute more to like these ideas. So you can reach me at last slide. Yep. That's my contact information. Slack, Reddit, Twitter. Take a screenshot. Thank you.
Outstanding. Thank you very much, Anthony.